Hi everyone, I'm Uma, and I'll be talking about a joint work with Srinivasan on trade offs between entanglement and communication. I'm unable to attend QIP in person, and I appreciate that you're listening to this recording and I hope you enjoy it. I'll start by giving a quick preview of our results. In this work, we study communication complexity and show quantum speedups over classical models that are equipped with limited quantum resources. We show in many settings that no matter how much quantum resource is given to a classical communication protocol, having even slightly more can give exponential speedups. I'll now start by introducing communication complexity. Communication complexity studies the amount of communication required to compute functions with distributed inputs. This is a field which has applications to many other areas, including circuit complexity, streaming algorithms, data structures, property testing, etc. Communication complexity is also a very useful lens to study quantum computation. Many famous quantum protocols, like superdense coding and quantum teleportation, can be viewed as communication protocols. Interestingly, communication complexity is one of the few settings where we can mathematically prove exponential quantum speedups unconditionally. All of this makes communication complexity a very useful lens to study quantum speedups. I'll now describe the communication model more formally. In the general setting, we have a function whose inputs are distributed between Alice and Bob, and they want to compute this function while minimizing the amount of communication. The function that they're trying to compute may be a partial function, that is, it need not be defined on all points. The players only need to compute the function on the points where it is defined. One simple communication protocol is to have Alice send her entire input to Bob. Bob then has enough information to evaluate the function, and this takes n bits of communication. The hope is that for some functions, the players can do much better by using quantum communication, perhaps use only polylog n qubits of communication. This is the basic problem of quantum versus classical separations in communication complexity. Sometimes we will talk about relational problems. Here, Alice and Bob get inputs as before, but now their goal is to output a bit string that satisfies some properties. Relational problems are a larger class of problems than functional problems, and it's often easier to show relational separations. In this talk, though, unless otherwise stated, all our separations will be functional. Let's now look at more specific models of communication. First, we have the classical randomized model, where the players can send bits to each other. These bits might be randomized. We denote this model by R. Additionally, we could impose various restrictions on the number of rounds. That is, the number of times that Alice and Bob take turns when communicating. In the most restrictive case, we have the simultaneous model, where Alice and Bob are not allowed to talk to each other. Instead, they send a message to a third party, Charlie, who must output the function value. This is called the simultaneous model and is denoted by the parallel symbol. A less restrictive model is the one way model and is denoted by 1. Here, Alice is allowed to send one message to Bob, and Bob must announce the answer. The least restrictive model is the two way model, where Alice and Bob can interact with each other. Eventually, Bob announces the answer. These are successively stronger models, and we know exponential separations between any two models. Now let's look at the quantum versions. There are two main types of quantum resources in communication complexity. One is quantum communication, and the other is entanglement. A priori, these are different types of resources. When we say quantum model, denoted by Q, we mean that the communication is quantum. So Alice and Bob can send qubits. The other quantum resource is entanglement, denoted by star. This means that Alice and Bob share entanglement, typically in the form of EPR pairs. We specify the number of qubits in brackets, and if we don't specify it, it is polylog n. We've now described the two kinds of quantum resources. By combining different resources, we get different models. Let's look at an example to clarify notation. Here we have Q parallel star K. Q denotes that the players send qubits. Parallel denotes that we are in the simultaneous model. Star denotes that Alice and Bob share entanglement. And K denotes that they share K qubits of entanglement. Here is another example. We have R2 star K. R denotes that the messages are classical. 2 denotes that Alice and Bob can communicate back and forth. Star denotes that they share entanglement. And K is the number of qubits of entanglement. Here, the classical messages that Alice and Bob exchange can depend on the measurement outcomes of the shared state. Now that we've defined the notation, we can state the main problem of interest, which is quantum versus classical communication. What is the power of quantum communication versus classical communication? This is a very interesting and well studied problem. There is a long line of research since the 90s which shows several exponential quantum speedups in communication complexity. We now have many examples of partial functions with a small cost quantum communication protocol, but no small cost classical communication protocol. The strongest result in this slide is due to Gavinsky and myself, Ran, and Avishai. These results show that quantum simultaneous protocols with a few qubits of entanglement can exponentially outperform two-way classical protocols. This shows that a relatively weak model of quantum communication can exponentially outperform a relatively strong model of classical communication. We ask, what happens if we give the classical protocol some quantum resources? In particular, what if we give Alice and Bob some shared entanglement? Can we still show quantum advantages over such models? First of all, entanglement is a powerful resource. One example of this is the quantum teleportation protocol. This protocol allows Alice to send Bob qubits using only bits, provided Alice and Bob share entanglement. More precisely, if Alice and Bob share one EPR pair, then sending one qubit can be simulated by sending one classical bit. In particular, if Alice and Bob have enough EPR pairs and at least one round of communication, then they can classically simulate all quantum protocols. But what happens if they only have a limited number of EPR pairs? Can they still classically simulate all quantum communication? This is the question that our work addresses. What was known before? In most previous works, the lower bound is only proved in the absence of entanglement. At best, those techniques could only give lower bounds against at most log n qubits of entanglement. In particular, all the functions in the prior works can be classically simulated using log cube and EPR pairs. We ask, how much entanglement do you really need? For some small k, think of k as polylog n, can we simulate all quantum communication classically using just k qubits of entanglement? Or is it the case that for every k, you can get exponential quantum speedups over classical protocols that use k qubits of entanglement? Our main result is to provide a strong positive answer to this question. We establish in a number of ways that no matter how much entanglement a classical protocol is given, having even slightly more can provide exponential speedups in the communication. Our first result separates q parallel star with k to the phi log cube n qubits of entanglement from R2 star with k qubits of entanglement. The best result before was a separation between q parallel star and R2 without entanglement. So our result improves the best known previous results by showing lower bounds that hold even in the presence of limited entanglement. We show that for a quantum simultaneous protocol, you cannot reduce the entanglement even by a small factor, even if you're allowed a lot of classical two-way communication. Just to remind you, the model R2 star can actually simulate Q parallel star if you give it enough entanglement. In particular, the function in our separation can be efficiently solved in R2 star model with k to the 5 log cube n EPR pairs. Our result essentially shows that these many EPR pairs are necessary. This appears to be the first technique that separates more entanglement and less entanglement in the two-way model. Such kind of a result was not known even for relations. Our second set of results is based on the R parallel star model. The first of these results separates R parallel star with k log n qubits of entanglement from Q parallel star with k qubits of entanglement. This result shows that you cannot efficiently reduce the entanglement in a simultaneous protocol, even if you're allowed to send quantum simultaneous messages. So, in the simultaneous model, quantum communication and entanglement are incomparable resources. The best prior result we had was a relational separation between R parallel star and Q parallel without entanglement. For partial functions in particular, it was unknown whether Q parallel star can outperform Q parallel. This was asked by Gawinski, and our result in particular answers Gawinski's question. Our second result separates R parallel star from R1 star. This shows that you cannot efficiently reduce the entanglement with one-way messages. This kind of a result was only known for relational problems, and we show it for functional problems. Finally, we also prove hybrid quantum classical lower bounds. We show that Q parallel star can exponentially outperform this model called R2 plus Q parallel. The R2 plus Q parallel model is a hybrid model where Alice and Bob first engage in classical two-way communication and then send a quantum message each to Charlie. The choice of this quantum message is allowed to depend on the classical communication. We show a partial function that is efficiently solvable in the Q parallel star model. However, in the R2 plus Q parallel model, requires either a lot of quantum communication or a lot of classical communication. To the best of our knowledge, these kind of quantum speedups over hybrid models were not known before. We now describe the functions in our separations. For all our results, the functions take the following form. Given a function f, we can define the XOR k version of f, denoted by f XOR k. Here, Alice and Bob get k independent inputs to the problem f. They need to solve f on all the instances and output the XOR of all the answers. Based on different instantiations of f, we get our various results. Let's look at these instantiations. The first instantiation is the correlation problem. It's not too important for this talk what exactly the correlation problem is, but I've just put it up for people who are interested. What is important is that this problem separates Q parallel star from R2. We show that the XOR k version of this problem separates Q parallel star with more entanglement from R2 star with less entanglement. I'll state this more formally now. We show that for the XOR of k for relations, this problem has a Q parallel star protocol of small cost with k to the 5 log cube n qubits of entanglement. However, any R2 star protocol that uses only k qubits of entanglement has exponentially larger cost. This is our first main result. Our second set of results is based on the Boolean hidden matching problem. Again, it's not too important what this problem is. It was shown that this problem separates R parallel star and R1. We show that the XOR of k copies of this problem separates R parallel star with more entanglement from R1 star with less entanglement. It also separates R parallel star with more entanglement from Q parallel star with less entanglement. I'll state this more formally now. We show that the XOR of k copies of the Boolean hidden matching problem has an R parallel star protocol of small cost with k log n qubits of entanglement, but any q parallel star or R1 star protocol with only k qubits of entanglement must have exponentially larger communication cost. Our third result is about hybrid separations, and this is based on the correlation problem. We show that the correlation problem has a q parallel star protocol of small cost. However, every R2 plus q parallel protocol requires exponentially larger communication. Previously, we only had a separation between q parallel star and R2, so our result improves the previous separations by showing a lower bound even in the presence of a large amount of quantum simultaneous communication. In particular, this shows that to solve the correlation problem, you really need entanglement. Now I'll move on to the proof idea. The high level idea is as follows. We take a partial function f that demonstrates some quantum versus classical separation, and we take the XOR of k copies of f. The hope is that since f required at least one qubit of entanglement to solve, f XOR k should require k qubits of entanglement. In particular, if you only had k over log n qubits of entanglement, then the communication cost should blow up exponentially. This is the main idea. The way we execute it is as follows. Suppose there is a protocol that uses less than k qubits of entanglement. In the first step, we convert it into a protocol that uses no entanglement and whose advantage is significant, at least 2 to the minus k. In other words, the success probability is at least half plus 2 to the minus k. In the second step, we prove an XOR lemma for f. Such lemmas say that given a hard function, the advantage in computing the XOR of k independent copies of this hard function decays exponentially in k. In particular, any protocol that has a significant advantage in computing f XOR k must have large communication cost. These two steps together give us the desired result. This is the overarching idea, but it turns out that there are some hurdles in implementing these. I'll now describe some of these hurdles. The first difficulty is in implementing step 1. Given a protocol that uses entanglement, how do you produce a protocol that doesn't use entanglement and still has a relatively large success probability? The usual idea behind such arguments is to replace the entangled state by the completely mixed state. However, this no longer works. It is possible for a protocol to be correct when using a particular entangled state, but wrong when using any orthogonal state. In this case, replacing the entangled state by a totally mixed state would heavily bias the protocol towards the wrong answer. So in particular, carrying out this step is quite non-trivial. We're able to do this for R1 star and Q parallel protocols, but for R2 protocols, we are not able to do this and we have to use an altogether different approach. I'm not going to describe that now. Let me instead describe step 2. The difficulty with step 2 is that XOR lemmas are hard to establish in general. The way we get around this is to establish XOR lemmas that are targeted for the correlation problem and the Boolean hidden matching problem. For the correlation problem, this was done in an earlier work with Ran and Wei. For the Boolean hidden matching problem, we prove an XOR lemma in this work. Let me summarize now. In this work, we prove quantum communication speedups over classical models that are equipped with limited entanglement. We establish in a number of settings that having even slightly more entanglement can provide exponential savings for classical communication protocols. This brings me to the end of my talk. Thanks for listening.